Hello and welcome. In this video, I'll be talking about building larger programs with a little bit more complexity. To start off, let's again use our live Google Colab session to implement the problem we talked about in the last video. We said we would try an open-ended problem, right? And the task was produce a program that generates the reverse complement of an input DNA sequence. And we made this diagram here. So let's finish things off and implement the actual program. And you can see I have my key here, so I'm just going to use that, but we'll talk about it as we do it. So the first step, of course, is going to be this input box here, right? We're going to add some kind of sequence, ATG, AGA, GCA, for example. And we have a reverse complementary sequence. That is initially empty. So you can make an empty sequence with a pair of quotations, and Python will understand this as a string, an empty string. So we can use this as a placeholder and build off of it. Then we start a loop. So we're going to loop through every base in our input sequence. We can just, for example, just print those out for now. So here's going through every base, looping through each base, and this variable base is then going to take on the values in the sequence. But we don't want that. What we want is to perform this part of the diagram here, right? We're going to perform a conditional check. We want to know, is the base equal to A, or is it T, or is it G, or is it C? And in each case, we're going to perform a different operation. So let's do that. If base equal to, let's say, T, and we add elif and we'll just change these, A, G, C. Okay, and we have another placeholder, so some variable called next base that we're going to set equal to the complement of whatever ingoing base we have. So let's do that. So we have a variable, let's call it next base equals G. Sorry, no, complement of T is A. Complement of A is T. Complement of G is C. Complement of C is G. And at the end of this conditional, we're still in the loop. We want to then append or add next base to our growing sequence, reverse sequence. And in this key here, you can see that we've just done this directly. So we've updated the value of the reverse complement here that we're growing. But here we can do this at the end of the conditional loop. That works as well. So, and we're still in the for loop, notice. So if you look at the indentations, we're still one indent in, but not inside this conditional statement anymore. So we're still inside the for loop, and we're just updating the value of reverse sequence by adding to it whatever next base got turned out to be. And at the end of this, if we print out reverse sequence, we should see that indeed T, let's see, this looks interesting. Okay. Oh, yeah, interesting. So this actually solved the problem. So what I was going to say is that, we add to our sequence on the end here, next base, and then we get a sequence that has complementary values. T corresponds to A corresponds to T here. And then we would need to do the additional step of reversing the sequence. So after Googling it, we figured it out. It's 2 colons and a -1. And then that would give us the reverse complement. So here we can see the T is corresponding to the A on the end here, the G to that C. But interestingly, on accident, I stumbled on another solution that I didn't think about, which is we could just grow the sequence in reverse to begin with. So always add the sequence that's growing to the next base. And this would also produce the reverse complement. So yeah, multiple paths to a solution. TAC, yeah, that's right. Yes, so that's one example. So from now on, we're going to be doing problems like this with a bit more complexity, and we're going to add a few more pieces. So one of these you've already seen is functions. Okay, so we've used already a bunch of functions, but then we're going to learn how to make our own. Another thing we're going to learn is nested structures. So we have we've already seen conditional statements that are occurring inside of for loops, but we can also have for loops occurring inside of for loops. So if you look at any piece of professional code, a lot of times you will see these nested structures, multiple indentations, and these are often operations happening on matrices, for instance. So let's go through some of these examples. So here is a for loop with a conditional. So yeah, this we've already seen. So this is a program that counts A bases in a DNA sequence. All right, so it's just going to go through each base, each character in the string. If the character is equal to A, increment the counter by 1. So this is a nested structure. We have a conditional that's indented because it's inside the for loop, and then if the condition is met, we have a double indented block of code that's here. So you guys have already encountered this. What you haven't encountered are nested loops. And a simple example is this. So let's say we have a string and we're looping through it. So we have our iterator here, char for character, which is going to take on the values A space ST or ING exclamation mark. But then for each of those, we're going to do a separate for loop. So every time for every single character, we're going to do another for loop. And this one is going to be on this list, just these numbers 1, 2, 3. And here we've named our iterator digit. So for in the first round, we're going through the letter A. We'll go through each then of these numbers in the inner for loop, 1, 2, 3. And if we print those out at the innermost point of this loop, we see that we're on A, we print out 1, on A, print out 2, on A, print out 3. And then only when we finish executing this inner for loop do we go back to the top of the original for loop and move on to the next item in the sequence. So in that case, it's a space. So then we get space 1, space 2, space 3. We move on again back to the top, now onto the S, S1, S2, S3, and so on. So that's that's a nested for loop. And here's an example of a problem that might require nested for loops. So make a program that generates a 100 by 100 matrix of approximately 90% zeros and 10% randomly dispersed ones. So here is how one might do this. So you have an initialization. So yesterday we talked about how you could make an empty matrix, a NumPy matrix of zeros using the numpy.zeros function. And here we have an outer loop. So for each row I in the range 0 to the number of rows in this matrix, we're going to do the following. So do what's inside. So for each of those rows, we have another loop. For each row, we do the loop for each column, j, in range 0 to the number of columns. And for each of those columns, then, we're going to do the following check here. This is an if statement. We generate a random number, and is it between, we generate a random number between 0 and 1. Is it greater than 0.9? So Python has a random number generator using the random library. So we can do this. And maybe it turns out to be 0.93 randomly. And so this satisfies the condition. And in that case, we would modify the element ij from this matrix, convert it into a 1, and then go back to the top of the inner loop and do this again for every single column. And then only when we'd processed all of the columns would we finally go back to the top of the outer loop and then move on to the next row. So it maybe makes more sense. We start out with an empty matrix, an empty black space here. And the outer loop is basically saying, first we're looking at the rows. And for each row, we're going to go through each column, each pixel basically in this matrix. And we have a random number. If it happens to be greater than 0.9, add a 1, convert it to a 1. And then when we finish that row, we go down to the next row. And then again, go through every single column. So this two loops here, nested for loops, is a basic way to navigate 2D data structure. If you have a 3D space, a 3D data structure, you could use 3 loops, a triple nested loop, for each row, for each column, and for each z-stack height, each layer. And you could do the same thing for a 3D space. So here's an activity. Consider a program that takes as its input a list of DNA sequences, strings. We happen to know for a certainty that one of the sequences is ATGGCCTA. The program uses a loop that goes through each item in the list, checking if the sequence is ATGGCCTA, and prints out the numerical position of that sequence in the list when it finds it. What I want you to try is create a slide in Google Slides, or just draw it on paper if you prefer, and use the rules that we've learned for creating flowcharts, and try to decide how you would structure this program. And let's talk about it. So here's my flowchart. Consider a program that takes as its input a list of DNA sequences, strings. So yeah, that's the beginning. We know that there's an input. It's going to be a list of DNA sequences, strings. Let's also look at the end. The program searches the list and finds a sequence and returns as output the sequence's numerical position in the list. So we know that the output is going to be some kind of number. Since we're looking at a string, we can probably guess that since we're looking at a list, we can probably guess that we're going to need to search this list. Okay, so we're trying to look for a particular sequence, ATGGCCTA. So we can make a loop then that will go through this list item by item and search for that sequence. So maybe the first time you make this this diagram, maybe you would put a big question here, but we know that we have to do something basically to figure out where in the list is our item. So that could be, version 1 of this diagram. Version 2 would be we look closer. So in the loop, we're looking at each item, right? We're looking at the sequence, and we want to know, is it equal to ATGG CCTA? And we know, of course, we can do that with a conditional statement. So we just check, is the item that we happen to be looking at equal to ATGG CCTA? And of course, we know item in this case is going to be the iterator, the iterable, the variable that changes when we specify our for loop. And if it's true, then we print out the position somehow, but what is this position? So that becomes the next problem. So maybe in version 2 of this diagram, you would print out this position here and then put a question mark next to, where do we get position from? So then we break it down even more, right? How are we going to get this position? Well, we know that the for loop, we can just go through the for loop in order, right? We can count, we can create a counter that starts with 0, and every time we go through this loop, we increment it by 1. So here we create a variable called pos for position equals 0, and on the first time through the loop, it's 0, but at the end of the loop, regardless of what happens in this conditional statement, we increment it up by 1. And then now the next time going through the loop, pos is equal to 1. So every time we're checking a new sequence, then we have a new position that's corresponding to it. So then we're able to print it out in this list. And here we can see the Python implementation of it. So we start out with this list, pos equals 0. We have the outer for loop for item in my list, the inner conditional statement if item is equal to ATGG CCTA, using, of course, the double equal sign for checking the truth of a statement, and printing pos, right? And at the end of the loop, not inside the conditional statement, but still within inside the loop. So we just have one indent here. We increment the variable pos by 1. So that's one way to do it. Functions. So you've already encountered functions, at least those that are made by developers. And we've used some of them. Length, len, to get the length of a list. We've used numpy.array just to create arrays, or np.array usually. Numpy.max, for instance, if we want to get the maximum value in an array, or numpy.sum or mean. So these are all functions. Type, we've used the type function to check, is something an integer. Math.factorial, we use this to compute the factorial. Print, we use print all the time. Print is a function. Now we'll learn how to make our own functions. So there's some simple rules that we have to follow. And we write def as in definition or define. So we're defining a function, and we can call it whatever, function A. And we supply an input parameter, variable A, for instance, and variable B. And we add a colon. And the function can do whatever we want it to do. Maybe we just add variable A and variable B, and we'll call this variable C, for example. And then if we want the function to return something, and it's actually optional, you can have functions that just does something and doesn't actually output something necessarily. Maybe it saves a file or something like that, but we can make a function that will produce a variable as its output. So here we can say var c is our output, and you use that with this return statement here. And then we run this, and by running it, we've just defined it. We've added our function to Python's namespace. And so now if we run function with some set of inputs, we will run the function now with this set of inputs. We can change then the inputs. In this case, we've just made a simple program that adds two numbers, the two inputs. It could be, we could make a function that multiplies them, 4 times 9. And you can also add optional arguments. So a lot of functions will have keyword arguments that have a default value. We could call this variable d. And maybe by default, it equals 100. We'll return as our solution variable c plus variable d. If we run this again, 4 times 9, 36, plus 100 is 136. And here I haven't supplied anything other than the first two, and that's because these keyword arguments are always optional. But if I want to, the user has the option of changing it. So we can change variable d to 200, and then it will change that. If we don't supply anything, it goes back to 100. So this is how you make functions, and yeah, this can be very useful. Here's a function version. So maybe we don't want to code up this whole thing every time that we did in the last exercise. So convert a DNA sequence into its reverse complement, but this time make it a function. So let's try that. And basically we can just copy and paste the code we've written, except instead of printing the sequence, what I'll do is I'll create a return statement. So let's create a function. Just paste this on def rev comp, and then our input sequence in seq is then the parameter that must be supplied to this function. And when you're defining a function, anything happening inside the function should be indented. So I'm going to select this whole thing and do one indentation here. And of course, in this case, we want our function to be general and to use a user-supplied input. So we don't want to go and define our input sequence inside the function. So we'll delete that and instead leave it up to the user to decide what the input sequence is. And then the last thing we add then is a return statement that is the answer that we computed, the reverse complement. And so then let's try it out. So to call it, we need to use the name revcomp, and it should take a string as its input. Let's try something simpler. And here we have our reverse complement. So there's a simple way then to make this quite useful bioinformatic function. Errors. So in Python, you've already encountered several types of errors, and errors can be revealing. So it's good to spend time kind of reading them. They can also be misleading sometimes. So sometimes you have an error that's happening in a library or in a function inside a library, and maybe the statement that's output is more about that function receiving the wrong kind of input from one of your lines of code. It might not point you necessarily to the right space, but oftentimes it does. So it's usually the first thing you do is to look for the line where the error is produced. Here we see that there's an error on line 2. And the type of error, you'll get an explanation. So in this case, we get type error. An integer is required. Got type str, a string. So here we've supplied the wrong input to this factorial function. We tried to compute the factorial of a string, which of course doesn't make sense. So Python output an error there. Up here, we have a syntax error. So we wrote a for loop here, but forgot to add a colon. And yeah, Python picked that up and produced an error. Type errors, cannot interpret 10 as data type. So numpy.zeros, it takes as its first input, when you want to make one of these zeros matrices, it takes what's called a tuple. It's just a pair of numbers in parentheses. So if we want it to be a 2D array, call this my dimensions. We could make an empty numpy array, a 10 by 10 numpy array, by using this tuple in parentheses here to specify the dimensions. But you'll get an error actually if you don't put them in parentheses. So this is a common mistake. So when you're trying to make 2D arrays in NumPy, people often put one set of parentheses when actually you need two here, because the input is this pair of numbers, not just one. Other errors, module not found error. So maybe we try to import BioPython, for example, and on Google Colab, if you don't install separately BioPython, you will get this error. It does not have it automatically installed. So that's why we always include this pip install BioPython statement when we're using these functions. Name error. So this one you've probably seen already. Anytime you try to use a variable without having defined it already. So here we did math.factorial of x, but x we never defined it. So we get this name error. Type error, factorial takes exactly one argument. So a lot of times specific functions will have errors that are generated that are specific to it. So some functions do take 3 numbers as their input, but the factorial function takes only 1. So if we try to shove 3 in there, we'll get a problem. Name error, NumPy is not defined. Of course, this will happen when you forget to import a module, for example. So yeah, errors can be really useful and good to Google as well. Quiz, so spot the bug in the following code. What type of error will result from it? So let's take a look at this. Import NumPy, data underscore x equals array parentheses square brackets. So the problem here, of course, we're going to get an error on this second line here, because we have tried to use this array function without specifying the library that it's coming from. And native Python doesn't have an array function. So we should get, I believe, a name error. But let's check that just in case. So let's just try array. Yeah, 1, 2, 3. Yes, name error. Name array is not defined. So it's not going to understand what this object is. Another one, what type of error will result from the following code? So what do we have? Var A equals 33, var B 56. If var A greater than var B, var C equals var A. Else var A less than var B. Okay, so the problem here is that, and this is very subtle, we should, if we have a specific condition, we should use the command elif here, right? Because else is just a catch-all. And when we're writing conditional statements, if we put else here, it should have nothing next to it except for just a colon. That's all other scenarios. But if we have a specific scenario, like this one, var A less than var B, then we should write elif. So I believe in this case, we would get a syntax error. So let's just try it and find out. And you don't necessarily need to know this. This type of thing will become more intuitive with experience. Else var A less than var B. C equals var B. All right, let's try it. And yes, we get a syntax error. And the reason it's a syntax error, of course, is because we're trying to create a conditional statement. And this is a syntax problem. We would have a syntax error also if we left out a colon, for instance. So Python understands that we're trying to do a conditional statement. It reads, for instance, that we have the word else here, and it understands what we're trying to do, but then it's confused by what's coming after. It's expecting just a colon. So that's a syntax error. Yeah, so Googling error reports can be very revealing. Try to find out, oftentimes you'll find people who have run into the same problem as you. Sometimes it's enough to just Google the end statement here, value error, x and y must be the same size. Sometimes you might need to specify the packages or libraries you're using. Maybe this is in the context of matplotlib, and you need to know, what happens, why do you get this error in the context of trying to make a plot, for instance. So here we've Googled value error, x and y must be the same size, pyplot, and then we get a bunch of answers, of course. Okay, and then this is finally a really nice feature. Oops. So there's a module called Pdb Python Debugger that allows us to go inside functions and play around with them and debug them in real time. So let's introduce, for example, an error in our revcomp, our reverse complement function. For example, let's eliminate a colon here, which should produce some kind of syntax error. Or yeah, actually no. Syntax errors get read when the function is defined. So let's create a more insidious error. Let's think about this. Let's see. Let's try this. We'll put a 1 here, and then see if Python, I think, will have trouble trying to add a number to this string here. So that should produce an error, and I don't think it will get detected when we define the function. Nope. So nothing so far. So this is a landmine waiting for us. So if we try to run revcomp now for some sequence, oof, type error. It can be hard. So, maybe we don't know. The problem is, we don't have access now to what's going on inside the function, right? It's kind of, the function is already saved. It's already in the namespace. So how do we kind of go inside and find out what's going on? What we can do is create a set trace. So we import this pdb module, and we can do this anywhere actually. Let's just do it up here. Import pdb, and we include this line here, pdb.setTrace. And what this will do is it will halt the program at that line where we said to set trace and create a live session inside that function. So now instead of hitting the error when we try to run revcomp, we hit the line where we put set trace, we already defined a sequence called revsec, for instance. Let's see. Should be empty. That's strange. And we have we should have our input sequence, and we're inside the function now. So I think it could be revsec. It's checking the namespace in outside of the function as well right now. So I think that's why we're getting an answer here. Yeah, that's a bit confusing. But the point is we're inside the function. We can step through it using commands. So n for next should go to the next line. And so now we're on this line in the function that was starting the for loop, for base in seek. And we can even check what is base. So we're on the first iteration. Are we? Yeah. What is base? Base is t. Okay, yeah. So I think this is again, this A here is remembering from the last time we ran this. But yeah, so now we've gone through the first line of that for loop, and we're still inside the function, and you know, we can check the values of things. We can still check in seek. We can check base is t. We can check rev seek. Yes, and rev seek is now empty. So it's really, we're inside the function, and we're at this line here, right? But we haven't run it. And you can keep doing this. You can keep stepping through and just kind of poking around, seeing what things are. We can see, we go to the first conditional, next base equals a. Yeah, and let's see, the next line there was if base equals t, and it was t. The first base in our input sequence was a t. So we triggered this first loop here, or this first condition here. And so now a variable called next base is getting defined as a. Let's hit next again. Now we're on the, looks like the second loop, so we can check what is the value of base. It's g now. And we're at this conditional statement, if base is equal to t. If we hit next, I think we'll move to the next condition. Elif base equals a. Well, it's g, so it shouldn't be that one either. Elif base equals g, yes. So here we trigger it, and we should see next base get modified. And indeed. So you can just keep doing this. You can hit C to continue, and this will go to the point where you hit the error. And you can also hit Q to quit out of this live mode. But this can be a really useful tool. So this is the Python debugger, and it's especially useful for functions, just poking around inside and troubleshooting. So this was a pretty long video. I'm going to end it here. So I'll see you in the next video.